We are Team Gagan Yatri, and the following statement is identifying hello CME events based on particle data from SWIS-ASPEX payload on Aditya L1. Now, there are several questions. What is hello CME? What is SWIS-ASPEX? And what is Aditya L1? This will be explained in the video. Now, our sun is very big when comparison to Earth. It has several factors such as it revolves faster on equator and slower on poles. For this, the magnetic field of sun is very cluttered, tangled, and unstable, and it releases a burst from the outermost layer corona, which is a burst of plasma, magnetic field, helium, and hydrogen. And this burst is known as coronal mass ejection. It has a greater impact on Earth, such as it destroys the satellite, it destroys the power grid, and makes a complete blackout on Earth, and the navigation, communication, radar systems are completely damaged. Now, to solve this, ISRO has sent Aditya L1 in 2023, which has 7 payloads, and one of the payload is SWIS-ASPEX, which is the meaning of solar wind and spectrometer on Aditya solar wind particle experiment. It is on L1 point, which is a Lagrange point 1 in space, at which the gravitational pull of sun and Earth is equal. Our model is very unique because it uses indigenous solution, all the data of ISRO, Bharat, Atmanirbhar Bharat solution. Second point, it has single payload dependency, as at this particular time, ISRO uses 4 payloads to calculate CME. We are only using a single payload on 4 factors to decide it is a CME or not, and it reduces the magnetic field measurements, which is a greater problem of ISRO, seen in the research paper. Now, our methodology is like this. From sun, hello CME occurs, it present on Aditya L1, which is measured by 7 payloads. Our model SWIS-ASPEX works on flux, density, temperature, velocity. It makes derived factors and calculations on moving average gradients. We remove the noise from the data and validate this data from Cactus NASA CME database because it has 25 years of solar data. Now, Aditya L1 is a solar observatory. We are using a train ML model by algorithms like XGBoost and neural networks, which increases accuracy and precision. We are identifying the threshold value, making CME, and identifying it is a CME, yes or no. Then there is a feedback loop for prediction of hello CME from the NASA database. Then we are extracting the feature, and the analytics dashboard reports, graphs, and alerts are shown to ISRO scientific community power grid operators. Now our model is feasible because, as I said earlier, it uses single payload dependency. We are using threshold-based approach, which is using clear region boundary for reliability in prediction. Next, it is compatible from different organizations such as ISRO, NASA, and European agencies. Also, it is economical feasible because there is an open source data channel of ISRO. The public data of Aditya L1 is shared, and the minimal software cost in the future when we are using cloud. And then there are major challenges of rare event, which is solved by synthetic overlapping damping technique. It is database dependency, which is solved by implementing regularization. A major problem is of single ambiguity and prediction error, which are solved by hyperparameter tuning using multiple models and moving averages for short-term fluctuations. It has 3 benefits: economical, social, and environmental. We are preventing multi-billion losses. We are also preventing the blackout by alerting 2 or 3 hours earlier. GPS, mobile networks, internet are relying on us, and also the satellites, which are prediction cyclones, monsoon, and long-term climate changes, are also served by us. Also, it has impact on space agencies, electrical power plants, which can rebalance the load on the power grid, scientific community, which can use our 3D model in our front end and our model, and also disaster management space weather for announcement and coordinating with infrastructure providers. Now, at the end, I want to conclude that we are not preventing the coronal mass ejection, but we are minimizing the damage of coronal mass ejection on Earth. Thank you. Now, here is a short video of our prototype, backend, ML model, and front end. These are the clips of the ML model training on 5 parameters: parse Cactus database, explore solar data, train CME classifier, evaluate model, and visualize parameters. These are the graphs of how our ML model is creating graph at real time from the SWIS-ASPEX data. We are importing all the data from our operating system, and our accuracy is 84%, which is very great in comparison to a single payload, and our model is prepared in 10 to 15 days. Also, our CME window evaluation at particular width time, it will approach Earth, it's 85%, which is very great. Now we are uploading CDF file or Swiss data, and at the real time, it will make the graphs of flux, temperature, velocity, and density. Here is our 3D model. It is taking some time to load because it is explaining all the 7 payloads of ISRO Aditya L1 satellite. There is a model VELC. This is our main SWIS-ASPEX model.